So hello everyone. Uh, Welcome to the session of applications, and we are going to have the first talk, which is a remote presentation, and the title is FastVer2, a probably correct monitor for concurrent key value stores. The speaker is Nikhil Swamy.
Thank you. I hope you all can hear me okay. This is joint work with several colleagues of mine.
Could you wait, please?
Hello? Hello? Do you hear me?
Yeah, it's okay. Please,
Okay.
please continue.
All right. Thank you. This is joint work with several colleagues of mine. Arvind, Arasu, Tahina, Ramananandro, Aseem, Rastogi, Aymeric, Fromherz, Kesha, Hietala, Bryan, Parno, and Ravi, Ramamurthy. The broader context for this work is a project that we have going called Project Zeta, where what we're looking at is how to reduce the trust a client has to place in a cloud service, both in the service itself and in any trust they may have to place in the cloud service operator. And specifically, we've been looking at in this paper at a key value store service called FastVer. FastVer is a state-of-the-art key value store developed at Microsoft Research. It's open source and it's used in several production services at Microsoft and elsewhere, and has been described in several papers at SIGMOD over the past few years. FastVer is quite complex. It has lots of optimizations for concurrency, and it's implemented in about 44,000 lines of C# and 13,000 lines of C++. It has several key features which I don't really expect you to read in any detail, but just for a sampling of it, it's got things like a latch-free, cache-optimized index, and so on. And all this complexity is in service of making it go fast, and it actually goes pretty fast. So here's a table from the FastVer paper. It reports a throughput of around 100 million operations per second, which it achieves because it's very concurrent, and that's faster than many other production databases out there, production key value stores out there, including, for instance, it's a order of magnitude faster than RocksDB, for example. So this is great. It's fast, but the question we're asking in this paper is it correct? In the sense of is it functionally correct? Does it respond correctly to every GET and PUT request? And further, is it secure against insider attacks? Which is to say that even if you believe that the implementation of FastVer is correct, does it behave robustly in the face of potential, say, admin attacks that involve tampering with the code or the storage of FastVer itself? Would a client notice if such tampering occurred? So that's a pretty demanding criterion to impose on FastVer. And to give you a sense of it, if you were to only consider the problem of its correctness, even that's quite daunting because it's quite a complex piece of software with lots of features. And the state of the art in proving the correctness of complex key value stores is still quite far away from being able to scale to something like FastVer. So here's a paper from OSDI in 2020 about a system called Very Better KB, which is a verified, crash-safe, sequential key value store based on a fancy state-of-the-art data structure called a B epsilon tree. It's implemented in about 6,000 lines of linear Daphne and takes about 45,000 lines of Daphne proof to get this to go through. But it's a sequential key value store, and it achieves a throughput of only about 10,000 operations per second, which is about 4 orders of magnitude away from FastVer. And of course, correctness of the implementation alone does not defend against insider attacks. So what we've been thinking about is, well, how can we rethink this problem somehow? What can we do to achieve the kinds of formal guarantees that we want about an existing complex stateful service? And the architecture that we are proposing in this paper is to use cryptographically monitored executions. And the idea there is that we attach to an existing service like FastVer a small monitor that runs separately from it in a trusted execution environment. And this monitor maintains an authenticated data structure that abstracts the entire state of the service. And we alter the service just a little bit to insert some calls into the monitor so that the service interactively convinces the monitor that the service is behaving correctly and responding correctly to client requests. And if the monitor is convinced of this, it can issue signed receipts of the certified operations that it has seen so far. So to give you a sense of how this works, so this paper is about formalizing this protocol and proving the monitor correct. So just to give you a sense of how this works, let me take a really simple straw man example. So I said the monitor maintains this authenticated data structure, abstracting the service's state. So for the moment, let's just think of this authenticated data structure as a hash of the entire state of the service. And this hash has a couple of special properties. The hash construction supports the following operations. It allows you to test if a given value v is the current value of some key k in the store. And it's possible to update the hash with a new value v prime for the key k. Okay, so that the hash supports these two operations. And a lot of the smarts in the paper are about how to actually construct a hash that supports these operations. So so now let's say the client requests puts the key 100, puts the value 100 with the key Alice. What FastVer does is it forwards this operation to the monitor, and the monitor is going to update its hash abstraction to record the value 100 for the key Alice. Now later, if some other client comes along and asks for the key of the value of Alice, then the FastVer forwards this to the monitor, and the monitor checks to see if in the current abstraction the value for Alice is indeed 100. And if so, it signs the operation that the client issued and forwards it to the client, and the client can be convinced that FastVer behaved as expected. Of course, if FastVer was to lie and provide the value 200 instead of 100, the monitor would notice that this is not the right value for Alice in the current abstraction and would refuse to sign the client operation, and this would be a verification failure. So that's a very simple setup. In reality, to make all this go fast and it be incremental and to support this hash construction, things are more complex. There are multiple threads in FastVer, and the monitor itself is multi-threaded, and each thread maintains a part of this abstraction. And there's an asynchronous API between the service and the monitor, supporting batched client requests organized into several epochs. The data structure itself combines several techniques, including a new sparse incremental Merkle tree and several per epoch multi-set hashes to build this fancy kind of hash. And so in reality, it's a little bit more complex. But the end result is what we have is a monitor that is configurable, concurrent, and fast. So the monitor is multi-threaded, and you can configure the threading in whichever way you like. So for instance, you can associate one monitor thread per service thread. The monitor maintains only a small amount of state to record these hashes, and the protocol is designed to minimize contention among the monitor threads. So monitor executions can actually be quite fast. I'm going to show you a little bit of performance numbers where we can get throughput in excess of around 10 million operations per second. And the monitor architecture is actually quite generic. So while we've applied it here to key value stores, we can instantiate the monitor with other kinds of safety properties and use it for applications beyond key value stores. And the other aspect and the focus of the paper really is that we've proven all this correct, and because of the way in which we deploy it, it's also secure against insider attacks. The main theorem says that a monitor certified trace is sequentially consistent, meaning that there is an interleaving of all the client operations so that every get returns the value of the most recent preceding put on the same key. The implementation of FastVer itself and its storage is untrusted because the only thing you have to trust for the correctness of the entire system is the monitor itself. And the monitor is protected by this trusted execution environment, and all its code is proven correct in F star. That said, and if it's not clear already, I'll just emphasize it. What we do is detect incorrect executions. We don't rule them out. So it's a runtime monitor. Just a glimpse into the performance numbers. So here it's a chart showing the throughput of a monitored execution of FastVer. The gray bar is a baseline number that we obtain by monitoring FastVer with an unverified hand-optimized monitor, and we get about 45 million operations per second in that setting. Our verified monitor is somewhat slower and achieves only about, in comparison, only about 10 million operations per second, but that's still faster than many production key value stores and 3 orders of magnitude faster than very better KV. So what we're doing right now is trying to find and close this performance gap between our verified and unverified monitor. And to give you a sense of it, we think half the overhead is due to our use of relatively slow cryptography in verified C code rather than hardware accelerated assembly code. So we think we can close half the gap by switching to better crypto. And then the rest of it is we're still trying to figure out how we can get this thing to go as fast as 50 million ops per second. But we think that's achievable. So the takeaway from this is that monitored executions can actually be fast enough to produce key value stores with end-to-end guarantees at a speed that's faster than existing unverified key value stores. Now, for the rest of the talk, let me just give you a glimpse into what the proof looks like. So the proof of FastVer is a refinement proof in 4 steps. The total executable code that we get out of our proof is about 8,000 lines of C code. The core monitor itself is compact, but which is what enables us to run it in the TEE. And but it's compact but subtle. So the core monitor is about 4,000 lines of C code. And we combine that with about 3,000 lines of parsers that we produce automatically from a tool chain called Everparse. That's a parser generator in F star. And we use existing verified cryptographic primitives from the Evercrypt cryptographic provider, which is also verified in F star. The total F star development to produce this much verified code was, it takes about 50,000 lines of F star code and proof. And that's about a 2-person-year effort. It was quite a subtle proof, and we found and fixed many bugs, both in the protocol specification and in the implementation. We found some bugs in the prior unverified implementation of FastVer. The way the proof goes is a refinement proof in 4 steps. At the highest level, we have a spec and proof in pure F star of a hybrid protocol that's describing this main hash construction that's combining this sparse incremental Merkle tree with this memory integrity checking based on multi-set hashes. There's also a cache protocol at this level, but it's a fairly unrealistic cache protocol, assuming a very large memory. So the first step in the refinement proof is to refine this cache protocol with a more realistic cache that supports that's indexed by 16-bit cache indexes. The next level of the proof is we switch representations and switch to low-level representations where, for instance, instead of using mathematical integers, we switch to using bounded unsigned integers, or using arrays of bounded size rather than infinite, unbounded sequences, and so on. And all of this is just semantic proofs in pure F star. There's no executable code in any of this part of the development. The final step of the proof is we switch to a DSL in F star called Steal, which is a concurrent separation logic based DSL. And at this level, our main theorem is a functional correctness spec against the higher level specifications. And the top level theorem is that monitors accept only sequentially consistent executions, except for Merkle or multi-set hash collision. So there's a lot going on in this proof, and the paper provides some more details. I thought I'd just give you one sort of reusable nugget from the proof in this talk. And that nugget is kind of a variation on monotonic counters, which, if you're familiar with separation logic, you've seen this kind of thing before, but there's a twist in the proof that we use for FastVer. So for monotonic counters, here's a simple picture of it. Let's say you have this picture in the middle depicts the history of values of a counter. And let's say you have a producer, and the producer is producing new values of the counter and is advancing this history at the tip. And the producer guarantees to only advance the counter. So if you have a bunch of consumers who have read prior values of the counter, each consumer knows that the current value of the counter is at least the value that they last read. So if the producer were to update this counter to, say, some new value, all the knowledge that the consumers have remains stable with respect to these monotonic updates by the producer. So this scenario has been studied a lot previously. And the twist we have on it here in FastVer is we have a notion that we call the anchored monotonic counter. So here, what we want to model is that the consumer's knowledge shouldn't lag too far behind what the producer is producing. So here in this picture, if the producer is currently at the value 42 and the consumer knows the current value, the consumer can anchor this current value, by which we mean the producer is allowed to update the current value to some new value that's not too far away from the current anchor. And if they were to try to update it to some value that's further away than the anchor, then the only way they can do this is by synchronizing with the consumer, agreeing on the new value, and they both advance their knowledge together to this new value. So it's this notion of a monotonic counter with a kind of a metric that prevents a consumer's knowledge or one participant's knowledge from becoming too stale. So what we have are some libraries in Steel where, given one of these pre-orders that describe how the counter evolves monotonically, and a relation that's describing this metric, the distance that a counter is allowed to be from the anchor, we build ghost state constructions that allow you to take stable snapshots of the monotonic state, and that behaves just like standard monotonic state. But the new bit is that there's a new kind of predicate that we have called an anchored knowledge, where if a client has anchored knowledge of the value of the counter at some value A, and they read the value of the counter, what they're guaranteed is that they get some value from the read that's a V, that's not too far from their anchored knowledge. So and dually, the producer is constrained to make only anchor preserving updates, anchor compatible updates to the counter. So with this construction, you may be wondering, how does this relate back to FastVer? The point here is that the way the FastVer invariant is structured, we have several producers. Each producer is a monitor thread, and we have one consumer, which is an aggregator thread. And there's a relation, an invariant that ties their state together. In particular, the aggregate state is synchronized with a frozen prefix of the state of each monitor. And if you parse this apart a little bit, what it's saying is that this involves a bit of monotonic state, because the aggregate invariant can only depend on the frozen prefix of the producer's state. But it's also got this anchor notion to it, because we require that the aggregate state is synchronized up to the frontier of the producer's completed up to the frontier of the producer's frozen prefix. So if you look at those two pieces together, what we really have is something like this anchored pre-order to structure the main invariant. So if that sounds interesting to you, do check out our paper. There's lots of details about how we actually build this anchored pre-order construction. Also in the paper is a way in which we build a safe API for this monitor so that we can use it safely from a trusted execution environment, allowing an untrusted client to call into this monitor without disturbing the invariance of the TE. And this then leads to our main theorem, which is you can call into the aggregator thread to find out the maximum certified prefix of the client interaction so far. And if it succeeds, it tells you that this conjunct of this specification tells you that up to a certain epoch, the interaction of the clients with the service are sequentially consistent, except for a hash collision. So just to wrap up, main takeaways from this talk are that cryptographic runtime monitoring can give strong safety assurances for complex services at a relatively low development effort, at a modest runtime cost, but the guarantees that you get are up to monitor rejection. The main spirit of this paper is about verifying the verifier and proving that the monitor is correct. And all the code that we run inside our trusted execution environment is formally verified in F star. We're currently scaling up our work to apply to beyond key value stores to other kinds of settings, like Foundation DB is a transactional store. And this paper is also a case study in the use of Steel, a dependently typed, proof-oriented concurrent programming language that gives you C code. So that's all I had. I'll stop there and see if we have some time for questions.
Any questions?
If I understood correctly, the clients don't talk directly to the monitor. So how do you stop the untrusted failing to send puts to the monitor, just dropping puts?
So the clients receive these signed receipts from the monitor. So if the service were to drop a put, then a client would notice that a put that it issued was not one of the signed receipts that it received, and at that point it would stop. It should stop interacting with the monitor, interacting with the service, because the service is dropping its operations.
Okay, so I know whether my put was actually accepted, but I don't get any guarantee about progress or liveness, so to speak. The untrusted thing could be non-live.
Oh yeah, there's a safety, and it's safety up to monitor rejection.
Okay, thanks.
More questions?
Hi, I was wondering, I mean, you mentioned at the beginning something about zero trust. You also mentioned quite a lot the trusted execution environment. So clearly there's a bunch of trust assumptions there. What exactly are the assumptions about the trusted execution environment?
Yeah, so the if you notice, there was two words, zero trust, in the name of the project. So yeah, I don't think truly zero trust is achievable. So the point is that we are willing to trust the code that runs within the trusted execution environment, and based on the formal theorems that we prove about it. So there's trust in the tool chain that produces the main theorem, and trust in the hardware that implements the trusted execution environment.
And I assume the C compiler has to be trusted to produce correct
Indeed.
assembly? Okay.
That's right. Yes.
And on the cryptographic side, I guess there's like a private key inside the trusted execution environment, which you're assuming doesn't leak or something like that.
That's right. Yes.
Okay. Okay. Cool. Thanks.
Any questions? Yeah, then let's thank the speaker again.